Okay, the next topic is the effect of low temperature aging on nickel-rich titanium nickel alloys. And just to get a little bit coordinated, first I'm going to talk about the annealed sample, show some DSC results at aging temperatures between 100 to 200 C with exposure times up to a month, go over some of the thermal properties, and show some microstructural changes associated with these changes, and then move on to a more device-relevant condition, and go over some thermal properties changes, and then the influence on mechanical properties. So again, some terminology which is a bit different from ASTM standard, which I'll be going through. I'm going to be using throughout my presentation a lot. Quickly go through it. We have the DSC on top. We have the cooling curve or the exothermic reaction going from austenite to R-phase to martensite. So the formation of R-phase, we call it the peak of it, we call it RP. The formation of martensite, MP. And then on bottom, the endothermic reaction or the heating reaction go from martensite. We revert the martensite, which is M star P, and then M or martensite or reverts to austenite, which is R star P. Again, I'll be talking a lot about MP and M star P, the formation of martensite, the reversion of martensite. The top one controls the upper plateau stress. The bottom one controls the lower plateau stress, and the difference between the two is the hysteresis, basically. So starting with a fully annealed sample aged at 200 C. On the left, we have the martensite formation, and the bottom, the dashed line is the baseline, and then 1 hour all the way to 127 hours of exposure. Again, we'll see there's a suppression of martensite peak or martensite formation as we expose it to 200 C. The same thing on the right as the martensite reversion peak going from the baseline, and we'll see the same suppression of martensite peak again. Now this is at 200 C. If we drop it down to 150 C, same behavior. On both sides, again, we see the suppression of both peaks, formation and reversion. Dropping it down even lower to 100 degrees C, the boiling temperature, boiling water temperature, still we'll see the same suppression on both sides. So this was interesting. And what is happening? Even at 100 C, we are seeing some changes in behavior. So if I put them all together and summarize them, on the left we have the formation versus time at different aging temperatures, and the reversion on the right-hand side the same way. And on both sides we see the suppression with aging temperature time combinations. So what governs it? What is happening there? We looked a little bit deeper inside the microstructure. These are on the left, we have the high resolution TEM from the baseline, and on the right we have the diffraction pattern, and it shows a B2 structure. Everything is clean, austenitic, no evidence of any precipitations that you see. By the way, these are the atoms that the high resolution TEM that you see. And now, aged at 100 degrees C for about 100 hours, we'll start seeing some formation of precipitates. And then on the left-hand side, on the 110 direction, we see some diffuse intensities, which is an evidence of nickel clustering, that the nickel is moving within there. So, which is a precursor to precipitation in that. So even on 100 degrees C, we have structural evolution in nitinol. Now moving on to a more relevant condition with a device that has, or a night node that has cold work, retained cold work, and it's heat treated, and look at the 100C exposure. Same thing, we see suppression of the Martensite peak on both sides, formation and reversion, and then now we have the R peak, but the R peak is unchanged, right? Again, looking at that, if I suppress these two peaks, that means that I have to get a increase in my plateau stresses, right? As the Martensite temperatures go negative, and that's what we see here, right? So the baseline is the dashed line, and then the other two exposed, we see based on that an increase in plateau stresses. Other than that, other properties, UTS, everything remain the same. Now going up in temperature at 150 degrees C, again, Martensite suppression on both sides. Now the R peak starts, it's moving too. It's moving to the right, and it's becoming more stable at higher temperatures. Again, looking at the suppression on both sides, one should expect an increase in stiffness or plateau stresses, which we see. And no changes to the UTS or any other properties, mechanical properties. Now at 200 C, suppression is there again. The R phase is becoming more and more stabilized at higher temperatures. And the mechanical properties, the plateau stresses go up and then come down again. And I'll talk about this in a moment, why that is. Now at 200 C, we also are changing some other properties. Some strengthening is happening in the material as well. And finally, at 250 C, the separation between the two peaks is at maximum. We still have the suppression on Martensite formation. Martensite reversion, however, it's following the R phase now. Something else is happening in there. And even though that we have suppression, the properties drop, which I'll come back to again in a moment. And again, just like the 200 C, we have the increase in UTS, some strengthening is happening in the material. But let me go back. I want to point out something really interesting. As an industry, we're obsessed with AF, right? Look at these two, the blue and the red curve, right? The AF, so what I have, the vertical lines actually are the body temperature over here. The blue and red lines, the AF of them, which is around here, it's about 50 degrees C. It's well above body temperature. And yet, you have superelasticity. Again, this is a confirmation that the AF is not what we're after, we should be after. It's the M star, MP, and M star that controls the mechanical properties. Just to summarize that, again, on the left, the Martensite peak is mostly suppressed. The M star P, the Martensite reversion peak, up to about 200 C is suppressed, and then we have an evolution of M star P. Now, we're not very sure about why that is. Is it because of the nickel clustering, it's the precipitates, or it's even the loss of coherency between the precipitation and the matrix? This is just to show the evolution of R phase. On the left, I have the RP versus time. And we start about 3-4 degrees all the way to 50 degrees. It's really remarkable. And then on the right, it's a separation between the R and M, starting at about 80 degrees, at peak of 180 degrees, which is really huge. So I pointed out earlier that the upper plateau stress doesn't really follow the MP, right? And why that is? If we want to predict the stresses based on with temperature, there are two terms that governs that, right? It's a delta T and it's a d sigma dt. Delta T is what we see. So if I suppress Martensite, this is going to increase, and my plateau stress should increase. But how about d sigma dt? In the case that we're stress-inducing Martensite from the austenite phase directly, the d sigma dt is about 6.97, let's say, max. But as the R phase becomes more and more stabilized at higher temperatures, the d sigma dt drops to about 5. And in the case that we're stress-inducing Martensite just from R phase, no austenite in there, it's about 4. So even though that we have a suppression of Martensites, that delta T goes up, the d sigma dt goes down, and as a result, the upper plateau stress drops instead of going up. So in conclusion, nitinol is metastable even at 100 degrees C. Exposures at 150 degrees C or less resulted in an increased in stiffness, which is due to the suppression of Martensite, formation and reversion, and that can be attributed to nickel clustering, precipitation, or loss of coherency and whatnot. And then at exposure times above 150 C, we saw a loss of stiffness, which is due to the d sigma dt that governs it. And because of the stabilization of R phase, we can have material nitinol that has AF well above body temperature and still be superelastic. And the last one is we have to be careful when we expose nitinol to temperatures around 200 C. And that's it. Any questions?
Quick question. So it seems like you stopped your testing at 100 degrees C.
Yes.
Could you comment what would happen if you had infinite amount of time and repeat this at a lower temperatures? Do you expect this to be a trend that
So I
continue?
stopped my presentation at 100 degrees C, but I did run some, and I'm still running some samples at 70 degrees or about a sterilization temperature 60, 70, and it's now about maybe 4 months in, 5 months in, and we don't see much of a difference yet. So I think the kinetics are so slow at that temperature that, yes, eventually it's going to change, but maybe in a million years or so.
So we have a lot of material in inventory, and a lot of that material is in inventory for quite some time. Would it make sense to retest some of the wire or tube after multiple years? And would you expect to see a difference there?
Well, theoretically, if we had it on the shelf for 100,000 years or something, maybe. But again, it's a good point. If it's we don't know if it's under stress or crimped at the temperature, what's going to happen to it. So yes, I would test it, but theoretically it shouldn't move much. Right.
Thank you, Lee.